Okay, this is 5.3, video C. We're continuing to talk about probability, conditional probability, using tree diagrams when it's helpful with sequences of events. This says that false positives and HIV testing, it should be noted that the percentages given in this problem are completely fictional, but let's say that suppose 1% of a population is infected with HIV. The probability of a false negative is 3%, and the probability of a false positive is 6%. Suppose that a person who tests positive for HIV finds that the probability that this person, we're supposed to find the probability that this person actually has HIV. Okay, so this feels like a conditional probability because we're saying given that they tested positive, what was the probability that they actually had HIV? Okay, so let's start with trying to see if we can construct making a tree diagram here. Okay, and just as reference here, a false positive is when a test says that you have HIV, but you actually don't. And a false negative is when the test says you don't have HIV, but you actually do. Okay, so we're going to start with the options are either a person truly does have HIV or they do not have HIV. Okay, and according to the percentages in the problem, it says that 1% of a population is infected with HIV. So that means there's a 1% chance of having it, then there would be a 99% chance of not having it. Okay, from there, it goes on and says the probability of a false negative is 3%. Okay, now remember, a false negative is a test says that you do not have it, but you really do. So we're in this branch here where someone really does have HIV, but we're talking about getting a false negative. Okay, so we'll put positive up here, negative down here, and we're saying there's a 3% chance of the test showing that they're negative for it despite the fact that they have it, which means there's a 97% chance that they are showing that they test positive if they have it. Okay, and then the other percent we were given is the probability of a false positive is 6%. That's if you don't have it, but then the test is telling you that you do. So here's 6% and 94%. Okay, so to answer the question that I have highlighted here, the question was, what is the probability that supposing that someone had a positive test result, that person actually has HIV? Okay. So this is a conditional statement, but I need to check and see, is the condition from my first column? If the condition is not from the first column, then I need to use the formula. Had the problem been the probability that you test positive given that you had HIV, well, now the given is from the first column, so my answer would just be found in the second column. Okay, but that's not what the problem's asking. So we won't be able to simply pull the conditional probability from the second column. We are forced to kind of set up the conditional probability formula, which is provided on the formula sheet. If you recall, it's the intersection of the two events in the numerator, and then the denominator is just the probability of the given. Now, these components of the formula, I should be able to pull from the tree diagram. So let's see if we can't do that. The numerator is supposed to be the intersection of having HIV and your test showing positive. Okay, the ands come from flowing through the branches. So we're doing 0.01 times 0.97. But in the denominator, I need all the scenarios that are ending with a positive test result. Okay, well, this situation ends with a positive test result, as does that one. So I need to place in the denominator the 0.01 times 0.97. That's a situation where they have HIV and they're testing positive. And then I need to put the 0.99 and the 0.06 because that also ends with a positive test result. No HIV, but still showing the test is positive. Okay, these would get multiplied, added together. Okay, you may not cancel these here for the simple fact that there is an addition sign there. That needs typed in very carefully into the calculator, and it would give roughly a 14% chance of that occurring. Okay, it says suppose that 10,000 people from the population were selected and tested for HIV. Okay, now the key here is they're giving you a number of people who they're planning on testing here. Okay, it wants to know how many would you expect from that 10,000 to have tested, to have HIV and test positive. Okay, now they're not asking you for a percent, they want the number. So if we can figure out the percentage or probability of people who would have HIV and be testing positive, we simply multiply that by 10,000. Okay, well we have that figure, that was our numerator right here in this conditional probability. So we would take let me write this down here. This is HIV and testing positive. Okay, that's the 0.01 times 0.97, which is 0.0097. Okay, that might repeat. Okay, so then I just want to figure out, well, how many of the 10,000 would that be? Well, I'm going to multiply those together. That's roughly going to give me about 97 people. Okay. All right, let's look at the next one here. How many of the 10,000 would you expect to have HIV and test negative? Okay, so HIV and have a negative test. I'm going to go to my tree diagram. I'm going to follow through the branches HIV, but I'm going to go this direction with the test being negative. That would be, to get the percentage, that would be 0.01 times 0.03. Okay, there's my probability, and then I will multiply that probability by 10,000 to roughly get that we're looking about 3 people would fall in that scenario of the 10,000. Okay, how many would you expect to not have HIV and test positive? Okay, so no HIV, and test negative. Okay, so we're flowing through here and down here. Okay, we're going to multiply those together, giving us a probability of 0.9306. Okay, and then I would multiply that times the 10,000 for a total of 9,306 people. Okay, I think we get the idea of how this is working. So I'm just going to pass over this last little part of this example and we'll move on to the next page. You'll notice on the next page, I actually completed a tree diagram for you. The question to this problem is what percent of teens are online and have a Facebook profile? Okay. You can look through that. We've done enough examples with the and of how you flow through the chart. I certainly would think that you would find maybe this a little easier way of coming up with the answer, but I did also show an alternate way of doing that as well. All right. Okay, let's go ahead and look down here at example 10, which again, I have created the tree diagram for you. We're just going to look at a few parts here to answering the question for this. Okay. It says about 27% of adult internet users are between the ages of 18 and 29. You can see I have that right here. Another 45% are between 30 and 49. And finally, 28% are 50 or over. The Pew Internet and American Life project finds that 70% of the internet users who are of the age of 27, I guess I don't have this fully completed, we need to fill this in. It says, have visited a video sharing site, so I need to fill that in as 70%, which logically means the complement would go on the other branch, 30%. It says 51% of those aged 30 to 49 are on the video sharing site, okay, leaving 49% who are not, and 26% of those 50 and up are. That leaves 74% who are not. Okay, let's try just a couple questions pertaining to this. What proportion of the adults who are of the age 18 to 29 and are that visit the video sharing site? Okay, so we are looking at what is the likelihood that you're 18 to 29 and you participate in the video sharing site. Okay, that would be multiplying through the branches, giving us 18.9%. Okay. This is having us do the same thing here for each of the age groups. Okay, we're calculating what's the probability that someone is in that age group and they're on the video sharing site. Okay, so again, this would just be going through the branches here. So we're going to fill this in here very quickly so we could look at the problem at the bottom. Okay, the problem at the bottom says, what proportion of all the adult users visit the video sharing site? Okay, well, that would be having to end here. Video sharing, video sharing, video sharing. That's actually this probability, and this probability all added up together. So we're asking what's the probability that all the adult users are basically participating in video sharing. Okay, and that would be these three values added up for a total of 49.13%. Okay, so we're going to look at the last concept kind of discussed here in Chapter 5, and this is the notion of independence, which is a very important concept that you understand. It plays a big role in things that we're going to be doing in the future. It also can be a little tricky, so we want to be able to discuss and have a good understanding of what it means when we say that two events are independent. Okay, two events are independent. So we're going to say if events A and B are actually independent, this means that the occurrence of one of those events has absolutely no effect, okay, no effect on the likelihood of the other event occurring, okay? So what this means is, the way we can kind of say this is, look, the probability given that event B has already occurred of event A occurring is simply just the probability of event A occurring. Okay, and I could flip it the other way. Okay. What this basically means is that the probability of A occurring isn't affected by the probability of B. Okay. So I'm saying given B occurred, the probability of A is the probability of B, and given that A already occurred, the probability of B is just the probability of B, okay? You'll notice this is not the typical conditional formula, okay? And that's because if two events are truly independent, it has no bearing that one of the events occurred first, okay? It mentions here when you're trying to prove that two events are independent, you do not need to prove both of these statements. You only need to show one of these statements, okay? So what we're talking about with independence is if we know that event B has already happened, it does not impact the probability of event A occurring at all, okay? So let's see if we can talk through a couple of things, because sometimes people get confused when we start talking about independence. They confuse that with mutually exclusive. Remember, mutually exclusive means there is no way for those two events to occur simultaneously at the same time, okay? Independence means if the probability of one if one event already occurred, the probability of the other event occurring has no bearing at all on the fact that the first event already occurred. Like, it's not changing that probability. Okay, so we're going to look at, here's our random phenomenon. The scenario is we're going to take a coin and we're going to flip it twice. Event A is that the first flip is heads, and event B is that the second flip is heads. Okay, the question is, are these events mutually exclusive? Okay, could we get the first flip being heads and the second flip being tails? Okay, that certainly could happen. So that means these are not going to be mutually exclusive, okay, because they could both occur. We could get heads on the first flip and tails on the second flip. But now, to check for independence, we need to ask ourselves this question: does knowing that we got heads on the first flip affect the probability of getting tails on the second flip? Well, no. Every time we flip a coin, it has the same probability of getting heads or tails. So flipping a coin is a great example of an event that is independent, heads or tails. Okay. All right, let's take a look at number 2. The random phenomenon is drawing 2 marbles from a bag, but we are not replacing the marbles, okay? So when you pull the first marble out, it stays out when you reach in the bag and select a second marble. It mentions here 4 of the marbles are black and 4 are red. Event A is defined as the first marble being black. Event B is the second marble is red. Okay, so the question is, are these events mutually exclusive? Could we select first a black marble and second a red marble? Yes, we could do that. That means these events are not mutually exclusive. Now, to say whether these events are independent, we have to ask this question: does knowing that the first marble was black affect the probability that the second marble is red? Okay. And the answer is absolutely, that impacts what the probability of the red, selecting a red marble, would be. Okay, and this is really hinged on the fact that we are not replacing. Okay, so if we pull out the first marble being black and it wasn't red, well, then we still have 4 red marbles left in the bag. If you told me that that first marble was red, well, now that's going to change my likelihood of the second marble being red. So it definitely impacts what that first marble is to say what the probability would be of your second marble being red. Okay, number 3, the random phenomenon. Select a single person at random from DHS. Event A is that they are a male. Event B is that they have long hair. Okay, can these 2 events happen? Could we choose someone who is a male and that person have long hair? Yes, okay, that is definitely a possibility. Okay, so since those 2 events could occur together, we're going to say no, those events are not mutually exclusive. Okay, now for the independence. Does knowing that a Dover High School student is a male affect the probability of whether he has long hair? Well, if I said to you, I'm going to pick someone at random and they have long hair, isn't there a higher probability that the person that I chose is probably a female? Knowing that that person was a male is probably going to make me think that the likelihood that they have long hair is a much smaller likelihood. So I'm going to say that no, these events are not independent. Okay? All right. Let's go on to number 4. The random phenomenon is to select one card from a standard deck. Event A is that it's a red card. Event B is that it's a club. Could I select No, it's just one card, not two. Could I select one card and that card fall into both of these categories, red and club? Okay, the answer is no. So that means those two events are mutually exclusive. Okay. Now for independence, does knowing that a card is red affect whether these two, does it affect the probability of it being a club? Okay. Well, yeah, if I know the card is red, I know there's a 0 chance that it could be a club. Okay. So are these two events mutually, or not independent? Okay. The answer is no. And here's the test that you want to show. Okay. This test up above right here. Okay. Where you show, given that one event has occurred, is the probability of the other event occurring the same as just that original event occurring? So let me demonstrate that for you here real quickly. The probability, we're going to say, given that the first card is red, that the second card is a club, if that equals just the probability that a card is a club, then we would know that these two events are actually independent of one another. But if I say, given that it's red, well, there are 26 cards that are red. Okay, 26 cards that are red. The probability of it being a club would be 0. Okay, now what's the probability of a card just being a club? Well, that would be 13 out of 26. These two probabilities do not equal each other. Therefore, I've kind of proven that they are not independent. Okay, the next random phenomenon, again, is selecting one card. Okay, we're saying the first card is red, the second card is a 7. Yes, those could occur together, so that means this is not mutually exclusive. Does knowing that a card is red affect the probability that it is a 7? So I'm going to try to show that these two probabilities are equal. If they come out that they are not equal, like this example up above, then I'm going to say they're not independent. Okay, so given that it's red, okay, 26 are red. What's the probability that it's a 7? Well, 4 of those, of the 26 red cards, 2 of them are 7s. The probability of just selecting a 7 altogether would be 4 out of 52. So I believe in both of these instances, these equal each other. They're reducing to the fraction 1/13. That means that these two events are in fact independent. Okay. All right, and then number 6 here. It says we again are selecting one card. The first card is red. The second card is a heart. Could those happen simultaneously? Yes, they could. So we're saying, no, these are not mutually exclusive. Okay, let me go ahead and show here that given that it's a red card, what's the probability that it's a heart? And is that the same as just the probability of selecting a heart? Okay, a heart card is, I think there are 13 out of 52. That would reduce to 1/4. Given that a card is red, so that's 26 red cards, what's the probability of those 26 of getting a heart? Well, half of them. Okay, this side reduces to a 1/2. So here I've shown, ooh, these are not the same. So that means that knowing that the first card is red is actually changing and affecting the probability of it being a heart. So I'm going to say that these are not independent events. They are influencing each other. Okay, so on this page here, and we're going to end with just this last example here. This is your test for independence. I did this right here. This is what I showed to prove that those were not independent. Again, you only have to show one of these two situations. It doesn't matter which one. So let's see if we can apply that to test whether two events that were given right here are in fact independent. Okay, we're given whether someone is right or left-handed, and then whether they are a male or female. It says, are the events male and left-handed independent? Okay, So I need to show, and it doesn't matter which one I'm choosing as my event A or my event B. I just need to choose one. So I'm going to say, given that someone is a male, I want to find what's the probability that they are left-handed. And if these are truly independent of each other, then that should just come out to equaling the probability that someone is a lefty. Okay, so let's do that part first. The probability that someone from this group of 50 is left-handed. Okay, we're just saying everybody all together. We're talking about the 50 people, but 7 of them were left-handed. So there's the probability that just I pick someone and they are left-handed. Now I want to use the table to come up with this conditional probability. So now I'm saying, given that someone is a male, so I'm exclusively just looking at those 23 people only, how many of those males are lefties? 3 of them. And I want to see, do these come out to the exact same probability if I punch those fractions into the calculator? And I clearly see I'm not getting the same number, so those probabilities are not equal to each other. So I'm going to conclude that these events are not independent. Being a male and being left-handed are